Okay, thank you.
Okay, so welcome everyone. I decided that this material at the end of the last lecture, it's better to start a new section with it. This will also mean that much of what we already did, we will now generalize, where instead of semi-algebraic, the role of semi-algebraic function is basically taken over by definable functions in some O-minimal expansion of the field of real numbers. So, because you might have been, it might have been a little strange why semi-algebraic turned up in this connection. Anyway, so we are going to fix a first order, once ordered language, extending the language of ordered rings. But we do want that there are no new functions. There are possibly new function symbols, but no new relation symbols, right? Of course, the language of ordered rings has less than as a relation symbol, but there will be not be any others. And then we will also fix we will fix a structure R tilde, which is an L expansion of the field of ordered field of real numbers. RL is my notation for the ordered field of real numbers. And then I let T be the theory of R tilde, which is a complete L theory. And I make two assumptions, namely that R tilde is O-minimal and that T, the theory of it, has quantifier elimination. So what I'm doing is actually cleaning up some material from papers 3 and 4 that I mentioned last time, where actually T is assumed to have, in addition, a universal axiomatization. But it turns out that that's not really needed. And I think it gives a more elegant development than what is in those papers in certain parts of it. So, of course, there are some standard examples. RL itself, of course, falls under these assumptions, where T is simply the theory of real closed fields. And then R sub n with this extra binary function symbol D for division, D of xy equals x divided by y, if x is in absolute value less than y, and y is not 0, and otherwise dxy is 0. And then R and x block. Again, you need log to obtain quantifier elimination, and you have to make some convention about what log is for negative, for non-positive real numbers. You set it equal to 0, say. Right, but now in a way, this second assumption is more of a convenience.
Don't you have the constant symbols of R in your language?
No, I don't need that. I don't need that. That's another way that what I say is actually more general a little bit than what I did before.
So you don't have 1/2 of your language, or do you? I mean, for instance,
right.
In R and X plug, you don't have 1/2.
Well, maybe indirectly. Oh no, in R and X, in Rn and R and X, you have all the constants already because they are special cases of restricted analytic functions. But yeah, but that's, yeah. Anyway, another way that it's a little bit more general, although that's not very important. Oh yeah, I was still saying something else about T. In some sense, the second assumption that T has quantifier elimination is more of a convenience because, of course, you can always extend your language or your theory by definitions so that the resulting theory has quantifier elimination. But there are natural examples where there is a natural language for which this holds, and these are 3 cases. Also, instead of this germs, continuous germs, we now prefer to work in a slightly, well, not a slightly, a bit much bigger ambient ring, namely the ring of all germs plus infinity of real valued functions whose domain is a subset of R containing some interval. So these functions do not have to be eventually continuous anymore. They are just yeah. Anyway, we also then for every function on the reals, we extend it to an Henry function on script G. Well, in a sort of obvious way, right? We f superscript G, if you plug in n germs, G1 up to Gn, then for large T, this will be capital F of G1T up to Gnt. Yeah. So eventually you have this equality. And again, it doesn't really matter which representatives G1 of these germs you take. This defines the operation F superscript G, the Henry operation on script G unambiguously. And actually, we of course do this also for function symbols. Here F is an actual function, but we do this also for an Henry function symbol in L, which again yields the corresponding Henry operation on G. In a way, we make G is a kind of L structure, except for the ordering relation. And it will be useful to introduce some terminology. Yeah, by the way, we often will simply drop the superscript G and you just have to think it, right? It depends on the context, whether we work with F itself or this extension of F to this Henry operation on G. Right, so we introduced the terminology, this terminology that a pair F comma G of germs is total if either Ft is less than Gt eventually, or Ft equals Gt eventually, which is the same as saying that F and G are equal as germs, or Ft is greater than Gt eventually, right? This will shorten. In previous situations, I often wrote all this out explicitly, but now I'm just saying the pair Fg is total, right? You can think of it as totally ordered or something like that. If you have another terminology that you prefer, let me know. This is the best I could come up with, total. Okay, so now we can introduce the analog of Hardy fields, although they are not necessarily fields, but only domains. So an R tilde domain, definition, an R tilde domain is a set D of germs, not necessarily continuous, although in practice they will be, such that for, first of all, for all pairs in this set, they are, all pairs are total. And it's closed under these operations Fg, where F an Henry function symbol, and Fg, G1 up to Gn. So it's closed under these Henry function symbols if D for all Henry function symbols F in L and for all n, of course, G1 up to Gn. D. Right. So, okay. Yeah, so if the, so for example, for R tilde equal RL, just the ordered field of real numbers, an R tilde domain would be just like a Hardy field, except the underlying ring doesn't have to be a field, but it's just a subring of. Oh, and also it's actually a bit more general because we do not assume that the germs in D are continuous, but they can be arbitrary. But otherwise, it's very much like Hardy fields corresponding to the case where R tilde is RL. So till further notice, we will fix D is an R tilde domain. We construe D now. We can now construe D as an RL structure. Yeah, we construe D as an L structure. How? Well, in the obvious way, F will be less than G for two elements in D, if and only if Ft less than Gt eventually. So this puts a linear order, a total order on D, because we are assuming that every pair of elements is total. And for eventually, and for n-ry, for an n-ry operation function symbol in L, how do you, the function that it names on D is simply Fg. It's simply the restriction of this n-ry operation on G to D. So in particular, D is an ordered, D is a subring, yeah. If you take for F 0, 1, minus, plus times, then you see that this means that D is a subring of G, and is totally ordered, and totally ordered by I less than, yeah? With D contained in, well, it's either an element in D if it is 0. If it's not 0, it has to be ultimately positive or ultimately negative, which means that it's a unit in this ambient ring. And that means that you have a fraction field inside G. So D has a fraction, has a fraction field. Frac D, which is a subring, which you can take it now as a subring of G. Right. Now, okay, maybe a remark. If all the germs in D happen to be continuous germs, then of course this fraction field is what we call the Hausdorff. It's in particular a Hausdorff field then. annotated C is a Outlook field. Okay, example. Yeah, so one remark again, we are going to often drop the superscript G in and D. Yeah, in describing the functions that are named by these function symbols, I use the superscript D and a superscript G, but I will often just omit them. But you have to always keep in mind the distinction between the symbols and what they name. Now an example. Since R tilde is O minimal, we have its Hardy field of definable germs of definable functions, and that is now an example of an R tilde domain. Tilde. Well, that is R tilde domain because it's basically closed under the operations of the primitives of R tilde. And now we can prove a lemma, which is, let me see, wait, I seem to be on the wrong page. Oh, wait, where am I? Yeah, one remark I want to already, that I can already make here is, yeah, okay. This is more a remark. Strictly speaking, we are not going to use it, but it's still useful to note that D, when you view it as an L structure, it may not be, of course, a model of T, but it is a model of the universal part of T. Yeah, this T for all is the set of all universal L sentences that are in T. Proof, let for all y, vy, be an element, yeah, belong to T. In other words, it's a yeah, well, y can be several variables, y1 to yn, and phi quantifier free, phi y a quantifier free L formula, and okay, then for all G1, of course, now we are not going to plug in numbers, real numbers, but germs from D, G1, Gn. We have R tilde satisfies phi G1T, GNT, eventually. For all sufficiently large T, G1T and GNT are defined. Yeah, so this eventually is only because we want the G1T up to GNT to be to have a sense. So you have to replace G1 up to Gn by representatives that are eventually where G1T up to GNT is eventually defined, and then this will hold. But if you think about what that, therefore, it follows that in D you have phi G1 up to Gn. Right? We made D into an L structure, so we can ask whether this is true. And if you think about what that means, you go back to the definitions, and you see that this is simply the same as saying that R tilde satisfies phi G1T of the GNT eventually. Right, so this is suggestive. This means it should be possible to extend D to a model of T, right? I mean, maybe, yeah, for those who have no background in model theory, they can skip this, or they can learn it from the Appendix B in our book, where we do all the model theory needed for this course. But D satisfying all universal sentences that are in T is the same as saying, is equivalent to saying that D can be extended to a model of T. And actually, the point here is that D can be extended to a model, to an R tilde domain, which is a model of T, right? And that's what we are going to do later on. This 412 lemma we are going to make a statement about eventual behavior with respect to zero definable sets. Yeah, so that is S in Rn be zero definable. Now this, when I say definable, I always mean in R tilde. And zero definable, yeah, in R tilde. Yeah, that's what zero definable means, for at least for today. Means zero definable R tilde. That means it's definable by an L formula, which do not use any particular real numbers as parameters. So it's just a pure L formula. And so then for all G1 up to Gn in D, yeah, either you can either GT will be in S eventually, or GT will be outside of S. Will be outside of S eventually. Where, of course, GT is what you think it is, I hope, G1T up to GNT. Right, so this is a bit like this earlier lemma on the eventual behavior of germs in a Hardy field with respect to semi-algebraic sets. But you see, it's zero definable is a little stricter, but in principle it's just as general, because by adding names for elements of the real numbers, for example, definable turns into zero definable. So in a way, this is more general than what we had before for semi-algebraic sets, where automatically all real numbers are assumed available as parameters. Proof, and it's quite simple. Well, it's certainly, well, first of all, if it's true for S and S prime, it's true for zero definable S and S for two such sets, then also for the union, intersection, and complement, then also for the union, intersection, and the complement of S in R. Right. And this means you can reduce to the case, because we have quantification, that S is given by an atomic formula. So this gives a reduction. The case where S is given by an atomic, defined by an atomic formula. So all the little s in R to the n, for which tau s is 0, tau is an L term, and the case, yeah, there are two cases. S is all the n tuples in Rn, and tau s is bigger than 0. Yeah. And tau y1 up to yn, an L term. Okay. Now for such, the point is now that for such tau, and G1 up to G and two n germs in D, we have tau of G1 Gn also in D, right? So D is closed under the primitives of under the function symbol, so also under arbitrary plugging it in an arbitrary term. So we have this is in D, and that means that ultimately wait, what am I doing? Yeah. Okay. So now we can use, that the pair tau G1 up to Gn, comma 0 is total. Yeah. In other words, tau G1 up to Gn evaluated at T is eventually greater than 0, or is eventually 0, or is eventually less than 0. And so that means that, well, if it's eventually greater than 0, that means that that GT will be eventually in this S, in the first S that I mentioned. And if it's, no, I got it wrong. If tau G1 up to Gn evaluated at T is eventually equal to 0, then that means that GT is in the first S that I mentioned here in the proof. And if tau G1 up to Gn evaluated at T is eventually greater than 0, then it is eventually in the second set S that I mentioned here. And of course, it can also be that tau G1 up to Gn evaluated T is eventually less than 0. Well, then it's in neither of these sets eventually. Okay. Oh, okay, good. Now, okay. Let me put a corollary here. 4 points. Let F from Rn to R be zero definable. Again, meaning zero definable in R tilde. And G1 up to Gn in D, then well, then the pair FG1 up to, yeah, then if you plug in these germs into, right, I explained how an n-ry function on the reals gives rise to an n-ry operation on D. So you get then FG1 to Gn. If you compare it to 0, you get a total pair, right? In other words, FG1 up to Gn evaluated that T is eventually greater than 0 or eventually equal to 0 or eventually less than 0. And the proof of that is now obvious. You apply the previous lemma to the following sets. Apply previous lemma. Yeah, the proofs, it's curious, but several of the proofs that took us effort for ordinary Hardy fields become almost trivial now. Apply previous lemma to the zero definable sets. Well, the first set being where f is negative is as in Rn, where f is less than 0, and then a set of all points where fs is 0 and s greater than is the set of all points in Rn where fs is greater than 0. So yeah, ultimately GT will be in either in this, or ultimately it will be in the second one, or ultimately in the third one. So okay, now we can do the analog of the real closure of a Hausdorff field. And so first let me define what I mean by the T closure, right? So this is the analog of the real closure of a Hausdorff field. The T closure, and I define it explicitly right away. The degree closure of D is the following. I denoted by D superscript T, like, yeah, instead of RC for real closure, we now put DT there. It's the union over all natural numbers n of the FG1 up to Gn, where f is 0 from Rn to R is 0 definable. It's 0 definable. And G1 up to Gn are in D, right? So, right, this is now certainly a subset of script G, but in fact it's an R tilde domain and a model of T. So this is the 4.1.4. Yeah, please interrupt me if anything needs clarification. Or so dt, yeah, is an R tilde domain. Of course, it contains T. It contains D itself. Did I write? because yeah, if you take for f the identity function from R to R and you plug in just an arbitrary element of D, you get that element back. So it's certainly dt. This contains, let me make that clear, is an R tilde domain, and it's a model of, as an R tilde domain, it is an L structure, and then you can ask whether it's a model of T, and it is. And it's the smallest, so to say, that contains D. Proof. Yeah, well, the previous corollary, if you apply a zero definable function to any n germs, you get something that's comparable to zero. But of course, since all the elements of dt are of this form, and you can always use dummy if you have two such things, fg1 to gn and f star g1 star up to gn star, you can always replace n and n star by their sum and so on. So you can always, and since we are in a ring, well, it's clear from the previous lemma that this is an R tilde domain, yeah? dt, an R tilde domain. Previous lemma. And now, okay, to get it's a model of T, we use a cheap trick, but I mean, it's a sort of thing that comes naturally to model theorists. We extend L to a bigger language, let's call it L hat, by adding for each zero definable n-ary function a new function symbol, by adding each zero definable f an n-ary function symbol, which for simplicity we also just write as f, right? Also denoted, written as f. So this is a bit of an abuse of language, but I mean, it's fairly harmless as long as you keep in mind the distinction between the function and the symbol. And we extend likewise T and extend T to T hat to T hat by adding for each such f a defining axiom, by defining for each such f a defining axiom, so to say, which defines the function symbol for all y, z. Well, it defines the graph, so to say, of f. Where VF is some quantifier free L formula. VF, YZ. Well, Y is usually, as usual, Y1 up to YN, and Z is just an extra variable. Is a quantifier free L formula, in the original language, defining F in R tilde, defining the graph of F, R tilde. Yeah, I mean, this is almost too silly for words, perhaps, but this is what we often do, and it's we just extend the language and the theory in a sort of innocuous way, but the point is that then this new T tilde it axiomatizes a universal theory. Okay, then okay, then the L hat theory axiomatized by T hat as a universal. Well, is universal. I mean, as a universal, has an axiomatization by universal sentences. We simply forced this. In some sense, these defining axioms are all they are all universal sentences in the new language, and probably that is already a universal axiomatization of the theory. Anyway, has an axiomatization by universal L hat sentences. Okay. Oh, yes. And now the point is that this dt this lemma that we proved about zero definable functions, well, now dt is not just before I do that, I have to introduce the corresponding expansion of R tilde. Let me. Yeah. So I also have to introduce R. Yeah, this is a little bit annoying notationally. R tilde, which is an L structure. Of course, it has a unique expansion to an L hat structure satisfying these new axioms. Yeah, is R tilde expanded to a model of T hats. Yeah, to T hats. Right. It's basically just R tilde where you give a meaning to the new function symbols according to the defining axioms that I wrote down. Okay, so, and now we can say, if you think about it, you will see that now we now dt is not just an R tilde domain, but even R tilde hat domain, not just R tilde domain. But even R tilde hat domain. If you, again, essentially because of this lemma that we proved before, or this corollary 413 that we proved here. Right. Oh, and now I see that I said before that this remark I made about an R tilde domain being a model of T for all, the universal part of T, wasn't going to be used, but in fact, that's wrong. I am using it here, namely, so by earlier remark, R tilde, sorry, dt viewed as an R tilde hat domain is a model of the universal part of T hat. Right? Imply, yeah, you apply this remark not to T, but to T hat now. And okay, but as we saw, T hat axiomatizes T, axiomatizes the same T L hat theory as T hat itself. Same L hat theory. That's T hat. Yeah, I'm a little bit. I use the term theory in a way that is perhaps not generally adopted, but for me, a theory is always closed under logical consequence, and so that's why I'm saying that T hat itself might not be a theory; it just axiomatizes a theory, and therefore that's why I express it this way. But T hat contains T, right? So that means that T satisfies T. Yeah. You see, it's just a matter of a cheap trick. But the curious thing is that this cheap trick now proves something that we last time for when we dealt with the real closure of a Hardy field, we actually had to do some math. And here we don't do any math, well, only trivial reformulation, so to say. So this actually gives the point is that we really exploit that T has quantifier elimination, while in that earlier proof, that the real closure of a Hardy field is again a Hardy, makes sense and is a Hardy field. We didn't really exploit fully the fact that the theory of real closed fields has quantifier elimination. I think that's the reason that this works.
Excuse me, now I have a question.
Yes.
Why is T universal? T hat universal? I mean, it contains.
No, I'm not saying that T hat is universal. It is. Oh, axiomatized by the L hat theory, axiomatized by T hat is universal.
But it contains T. So
yes.
But T is not universal.
You're right. I'm not assuming that T is universal, but I'm adding all these defining axioms which are universal, and they are already strong enough, perhaps with a few other. Yeah, I think they are probably strong enough to axiomatize also T. Yeah, if you think about it, these axioms, these defining axioms are strong enough to actually also take care of all the function symbols that were already there.
Okay, yeah. I mean, you added all zero
Anyway,
definable functions. Okay.
These
Yeah.
universal axioms already axiomatize all of T hat and therefore also T.
Okay. Okay.
Yeah, well, anyway, that requires a little, I agree that it requires a little bit of thinking, but it's not,
Okay.
not a big deal. Yeah, now this cheap trick also gives you the following, at least one direction of the following corollary. Yeah, so you can also ask, well, what about when is D a model of T? D being an R tilde domain, right? Well, this is exactly when, if and only if the result of that lemma, let's say, if it's closed under all these new entity operations, F, T1, Tn in D for all zero definable. For all zero definable F Rn to R and T1 to Tn D. Right. Yeah, let me say about the proof that this direction use the same arguments as for the cheap trick. Use cheap trick. And for the other direction, well, you have to do a little bit of work exercise. Right. Yeah, and so we get now also this corollary together with our construction of dt tells you now also an analog of what we said about the Hausdorff, the real closure of a Hausdorff field. dt is the smallest. Again, this is with respect to inclusion. Smallest tilde domain with respect to inclusion. That contains D and is a model of T. Okay, model of T, right? Yeah, so that involves, that is the, you have to use this corollary that I just mentioned. And then you see this immediately. Okay, so now, yeah, let me again mention the obvious example. Hausdorff fields are in particular R11 domains. Well, they are exactly the R11 domains whose underlying ring is actually a field. R11 domains. And for the Hausdorff fields, HRC is simply the T closure, is what we call here the T closure of H for T is the theory of RL, which is of course simply the, axiomatized by the theory of Liu closed fields, yeah? Axiomatized by the usual axioms for Liu closed fields. And so you see, this gives a different proof of this business about the real closure of a Hausdorff field, which is basically almost trivial compared to the original one. And it simply is that we exploited the assumption of quantifier elimination in a much in a better way. Okay. Aha. Exercise. So this is another analog with a fact about Hausdorff fields. If f from Rn to R is zero definable, and this is really an exercise in using a little bit of O minimality, and G1, Gn are in D, but also CR. Yeah, they are R times continuously differentiable germs. And R is now a natural number. Then F G1 up to Gn, which is of course also, which is now an element of D, which of course we know is an element of dt by definition, but it's also a CR germ. And I will actually come back to this exercise. I will basically show later an argument that basically shows you how to prove this. If corollary, but let me mention a corollary now. If R a natural number and D consists of CR germs, then again dt, the T closure, can also consist of CR germs. You do not lose any smoothness here. Okay, so this is now we go to subsection 4.2, adjoining a germ to an R tilde domain. Yeah. Adjoining. This is again an analog of what we did for Hausdorff fields. Adjoining a new germ R tilde domain. And this uses using a little bit of model theory. I mean, the previous argument you could say is also model theory, but it's just the definitions of, and there is really no serious model theoretic argument involved. But here we use model theory slightly more seriously. And again, for those who are not familiar at all with model theory, our book has Appendix B, which contains all the model theory for this kind of stuff. Okay, so we are going to introduce a big elementary extension of R tilde, and even a bit more. Let M less than B. It has to be, I'm going to assume that it's sufficiently saturated, and again, yeah, D D plus, this symbol is simply the next cardinal, the the least cardinal bigger than the cardinality of D. Yeah? It's the least cardinal bigger than the cardinality of D. Saturated elementary extension. Yeah, we just introduced a big model of our R tilde, elementary extension of yeah, it's not, it's actually a bit more than R tilde. It's R tilde where you also have for all functions from R to R. Yeah, we want somehow all germs to be present in R tilde. So we just expand it by all. This is more than enough, but we just take all unary functions from R to R. So here the G's are not actual germs, they are actually totally defined functions from R to R. But of course, all germs are represented by such functions. And let A be some element of M, which is bigger than all the reals. Yeah, A bigger than R. So yeah, right. M is some big real closed field with extra structure. It contains, it's an extension of R tilde, and so there will be plenty of elements that are bigger than all the real numbers in M. And now we can define a map from iota RA from G into M. Well, actually into, yeah, in the underlying set of M. For the moment, it's just a set theoretic map. And how is it defined? Well, if you have a germ G, what do? You make it into, you take a representative of it, a function from R to R, call that also G. And then you interpret that G as a function on M and evaluate it at A. Right. So maybe I should explain then there are two G's appearing here. On the left, iota AG, G is just a germ from script G. And on the right, G is a representative of that germ, or strictly speaking, the name of that representative in this structure R tilde G. And then this name is then names a certain function from M to M. I hope this is not too confusing. Yeah, maybe I should write out the last thing where GM of M to M is the function the function named by some named in M by some G from R to R, representing the germ G on the left. We use G because it's annoying to have to change notations all the time. So there are at least 3 G's here: the germ, the representative of it, and then also the name of that representative in the language, which is linguistic thing, and then what it names in, and then the function on M that it names by some G representing the germ G. Okay. Anyway, of course, when you are used to such things, you automatically work with these things without any trouble, but in the beginning, if you learn model theory, you have to make sure that what you're talking about. So routine verification. This iota A is basically a homomorphism of L structures. Routine verification. If you apply iota A to F G, well, G1. Fm of iota A G1 for any capital F in L, function symbol, for any germs in G now, yeah, not just in, right. I haven't introduced any particular R tilde domain yet, but well, D is all, in the background there is a D named, I fixed an R tilde domain D earlier on. So, and then iota A, when you restrict it to D, is actually an embedding. Iota A restricts to an embedding. That means it's in particular from D to M, script M now. Why is it an embedding and not just a homomorphism? Well, if you have G bigger than 0 in D, since G greater than 0 in D, yields iota AG greater than 0 in M. Yeah, why is that true? Well, remember, G is a germ, but it's represented by a function from R to R, which is ultimately positive, right? But if G from R to R is ultimately positive, that means that if you take G superscript M, yeah, the corresponding function from M to M, it will be positive for all arguments that are bigger than all real numbers, right? Ultimately, positive means positive whenever the argument is bigger than some fixed real number, but of course, all elements of M that are greater than all of R will certainly satisfy that condition. So that's why, that's why this last statement here is true. G greater than 0 in D yields iota AG is greater than 0 in M. And that means in particular that it's an embedding of L structures. Right. And so, so this is a useful way to think about germs. You simply replace it by the value of a representing function in some elementary extension evaluated at some infinitely large number. Okay. So D is then isomorphic via this iota A to its image in this is now an L substructure of M. Right. Moreover, if T is a model of T, this yields the isomorphism D isomorphic to iota AD. It's now an elementary substructure of M. Again, with respect to the L language as an L structure. Yeah, since T has quantifier elimination, T has QE. If you have two models of T, and one is a substructure of the second one, then it's actually an elementary substructure, right? So, and we are going to exploit this to prove the following proposition, which is we use this to, let me see, what is the time? Aha. So I have.
Now, may I interrupt by a little question?
Yeah,
Yeah,
sure.
so far, have you used the saturation hypothesis of
No, not yet.
Okay.
Well, only in a very mild way, I guess, by not explicitly. I took let A and M, A bigger than R in M. Certainly, if M is saturated, there are plenty such A's.
Right.
But otherwise, I didn't use it.
Okay.
But now I'm going to use it. Use this to generalize.
Okay, thank you.
An earlier fact. About adjoining germs to Hausdorff fields. So we go to the whole previous stuff now, but in a very rapid fashion, so to say, and see how everything generalizes in a very cheap way. So generalize about adjoining germs to Hausdorff fields. Four to one. Suppose, so in that earlier fact, we were actually assuming that we had a real closed Hausdorff field and then some germ outside of it, continuous germ, which with every element in that Hausdorff field forms the total pair, right? Suppose D is a model of T, so that is the analog of being a real closed Hausdorff field. And we have a germ now. And suppose it is, if you form any pair G, H with an element in H and D, and GH is total for all H and D. Yeah, in other words, GT is eventually bigger than HT, or eventually equal to HT, or eventually less than HT. Then I can explicitly introduce now a certain subset of G, dG. It's like the L structure generated by G over D. So I'll put it this way, is I take all L terms and I plug in any elements of D together with G, tau y1 and 2, yn comma y, an L term, and G1 in G. Yeah, for all n. So maybe I should write here, I should have inserted a union n symbol. Right. So then this is an R tilde domain again. Yeah, so G generates an R tilde domain over D. And you can think of it that way. Yeah, the R, you can think of this as the R tilde domain generated by little g over D.
Now
Yes.
G1, Gn are in D now, I think.
Yeah, you're right. That's what. Yeah, of course. Thanks. What? Yeah, thanks. Right. Okay, so now we are going to prove this. Well, one case is trivial if G is already in D. If G in D, then what I defined here is simply D itself. And we are done. There. So assume G is not in D. Below. Let A comma B in M, A, B, both bigger than R. The thing is, I have to show that A and B behave in the same way when I apply these iota A, iota B maps. A, B bigger than R in M. Then we have a commuting diagram. Well, D, iota A into iota AD. Iota B, iota BD. Well, and I just, since these iota A and iota B maps are isomorphisms, I can of course make a commuting diagram this way, right? In other words, iota AB is simply, you go from iota AD back to D via iota A inverse, and then you apply iota B. And so these are L isomorphisms of L isomorphisms. Now for all F in D, what do you get the following equivalences. F is eventually less than G, right? That means Ft is less than Gt eventually. That of course is the same as iota AF less than iota AG in M, as we have noticed before. Oh, I can actually shift, but then I get Okay, but this iota, but it's also equivalent to iota BF less than iota BG in M. Right, so what this means is that iota AG and iota BG realize cuts in iota AD and iota BD that correspond under this isomorphism. So iota AG and iota BG realize cuts in iota AD and iota BD corresponding under the isomorphism between them. Yeah. Okay, but then you see, O minimality then tells you that iota AB can be extended to an, therefore, yeah, and here I have to assume some model theoretic knowledge of O minimality. I don't know if this has come up in Gerrit's course, but O minimal fact about model theoretic O minimal fact, iota AB extends to an L isomorphism. Yeah, we are in some very big model script M of T, and you have two elementary submodels, iota AD and iota BD, with an isomorphism between them, and two elements, iota AG and iota BG, which realize corresponding cuts. And then that means that iota AB extends to an L isomorphism. Iota AD, where you now adjoin the germ, not the germ, the element iota AG. In the well, let me write here L hat, because we are now close. We basically take the model that iota AG generates over iota AD in the ambient model script M. Iota BD, iota BD, L hat. Between, yeah, let me explain this notation L hat. Again, it simply means you close off under the L hat operations between the elementary substructures of script M generated over iota AD and iota BD by iota AG, iota AG, iota BG, respectively. Yeah, well, this is one of the nice things about O minimality, model theoretic things about O minimality, that you can do this. And that means that, in particular, this means for all L terms, even for all L hat terms, but let's just stick to L terms. Therefore, for all L terms tau y1 up to yn comma y and g1 and germs g1 up to gn in D. What we get here is that the sign, yeah, you can consider iota a of tau g1 to gn comma g, and you can also look at iota b of tau g1 n comma g, but they have to have the same sign because they correspond under this L isomorphism that I indicated here higher up. Yeah, so the sign of this has to be equal to the sign of that. In other words, these elements of M are either both positive or both 0 or both negative. And what this means is that, and that means in particular that this sign is independent of the choice of A. Yeah? So this sign is independent of the choice of A. And if this sign is -1, yeah, that simply means that, yeah, if this sign is -1, we must have, that means that for all A greater than R in M, iota A tau G1 up to Gn comma G is negative. But that can only happen if tau G1 up to Gn comma G is evaluated at sufficiently large t is negative. You must have tau G1 to Gn comma G t is less than 0 eventually. And if this sign is 0, then likewise tau G1 t is 0 eventually. Yeah, right. And likewise, if the sign is +1, right? So this is, of course, a key step here. The sign is independent of the choice of A. Yeah, and if it's -1, you must have this because, yeah, here we use well, I guess you could say we use here saturation in the sense that if tau G1 up to Gn Gt is not less than 0 for arbitrarily large t, that means that by saturation there must be elements A bigger than R for which tau G1 up to Gn comma G evaluated at A is also not less than 0. But right, but this iota A tau G1 up to Gng is really tau G1 up to Gng evaluated at A. Yeah. So okay, so this is really the argument that R tilde that let me see, where are we in the proof? Yeah, this is the proof that it's an R tilde domain. I mean, it's certainly closed under the that it's closed under the primitives of the language L is clear from the definition. So we only had to show that any any such element is together with 0 is total, and that's what we proved here. Right. So tau T1 T is total, comma 0 is total, which is all we. Okay. Right. So you see, again, this is a rather different argument from what we did for Hausdorff fields. And if you are used to model theory, this looks that you are almost doing nothing. Well, of course, you are exploiting O minimality and facts about it. Okay, so now we can start with R tilde Hardy fields. 4.3. Okay, well, first of all, let me say what an R tilde Hardy domain is. Is an R tilde domain whose germs are now C1, D contained in C1. Yeah, so we are assuming that they are continuously differentiable germs, such that if you take the derivative of such a germ, you get, again, you land back in D. Yeah, so hence, so D is then actually automatically not just consists not just of C1 germ, but Cn germs for every n. So, right, and an R tilde Hardy field is simply one R tilde Hardy domain whose underlying ring is a field. And that's what we are going to consider from then on, an R tilde Hardy field is an R tilde domain whose underlying ring, a subring of script G or script C if you want, whose underlying ring is a field. Yeah, so for example, an RL Hardy field, yeah, RL being the ordered field of real numbers, an RL Hardy field is exactly a Hardy field, exactly the same as a Hardy field. Right. Now, example, HR tilde, yeah, this Hardy field of definable germs of definable functions from is an R tilde Hardy field. Well, we already mentioned that it is an R tilde domain, but because of definable functions being eventually C1 and the derivative also being definable, you see that it's actually an R tilde Hardy field. And so, right, In fact, it's the smallest R-tilde-Hardy field containing all real numbers and also the germ of the identity function, and which is also a model of T. Yeah. R-tilde-Hardy fields. R, X, and being a model of, yeah, not containing that is a model. R, X, and that is a model. Okay. Right. Any, yeah, of course, any R-tilde-Hardy field that's a model of T is in particular a real closed Hardy field, right? Because T extends the theory of real closed fields. Right. And now we can prove the yeah, now we are going to generalize the fact that the real closure of a Hardy field is again a Hardy field. So here is the proof, or here is the, it's really, let me see, yeah, 431 lemma. Let me see, I have, oh yeah, okay, I think that should take not more than 10 minutes, so I can stop 5. Yeah, lemma. Suppose D is, oh yeah, suppose D is an R-tilde-Hardy domain. Yeah. Then its T closure is an R-tilde-Hardy field. Right. Any model of T, of course, is a field, so that is rather proof. And here I'm basically also giving away a hint for doing this earlier exercise about if you have a zero definable n-ary function on the reals, you can plug in any CR germs from an R-tilde-Hardy domain, and what you get is again a CR germ. So let F from Rn to R be zero definable. And G1 up to Gn in D. And what we have to show is, yeah, so an earlier exercise already claimed that if you plug in G1 up to Gn into F, you get an C1 germ. Yeah, an earlier exercise. Already, but I'm actually giving you the hint. Exercise already claimed that an F G1 up to Gn is at least a C1 germ. Yeah. Or actually, since the G1 up to Gn are CR for every natural number R, it will actually be a CR germ by that exercise. But that's the, yeah, okay. But if in fact the arguments we are going to give, we are about to give, the argument about the argument for what? The argument we are about to give for this, the derivative of this germ to be also in dt. Is basically the same as that, which also as that giving that this is C1 in the first place. C1 first place. Okay, so what we do is really exploiting an O minimal factor, namely that zero definable functions are piecewise C1 or even piecewise CR, but what exactly does that mean? We have to, yeah, by O minimality, we have, yeah, the pieces, we cover Rn by zero definable pieces, zero definable S1, comma, Sm, covering Rn. Oh, and they are subsets of Rn. And we have zero, yeah, and we have also zero definable open sets around them, open U1 to M, around these S's, yeah, with S1 and finally C1 functions, zero definable C1 functions on the use F1 in C1 U1 up to Fm C1 UM, such that F agrees with Fi on Si, such that F equals Fi on Si, right? So that is an accurate version of stating that zero definable functions in an O minimal expansion of the reals are piecewise C1. Okay, and now, okay, G1 up to Gn are in D, so they define, so they will, G1T up to GNT will ultimately lie in one of those SIs. So take I, take one of those such that, so here we exploit an earlier fact that GT, G1T to GNT will ultimately lie in SI eventually. Right. Okay, then So, okay, so then what this means is that if you now plug in to do this, will be Fi of G1 T to F GNT eventually. And now Fi being C1 on this open set, we can take the derivative, therefore, right. This is now G1 up to Gn are eventually C1, since they are elements of a R tilde Hardy domain, and Fi is C1, so you can take the derivative F G1 Gn prime is, well, then the chain rule J is 1 partial Fi partial Yj G1 okay, Gn Gj prime, right. Okay, maybe I omitted a little step here, but I'm sure you can fill it in. But this is now the partials of the Fi with respect to Yj are again zero definable functions. Well, they might not be totally defined, but you can always extend it to a zero definable function, which is totally defined. And then we know that this is therefore an element of dt. All the n terms here are in dt, and the gj prime are in d. So therefore, ft1 prime is in dt. And so we have proved that dt is indeed closed under the taking derivatives. Right, there was one other thing that I also wanted to cover. Right. There is one more, two more items that I want to cover, but I think I should stop and simply do that next time. But you see that a lot of things that we did for Hardy fields, we now know for R tilde Hardy fields, and actually in a rather cheaper way than we did earlier. Okay. At least if you use a model theory, yeah.
Thank you, Lau. I stopped the recording.
Okay, yeah. And there is no, yeah, I don't have an exercise session after this. It's other